Welcome back. Today we are going to make this topic feel simple, visual, and useful. By the end of this lesson, you should not just know the rules. You should understand why they work. Here is today's roadmap. We will focus on fractions, order of operations, ratios, and proportions. For each concept, we will build the idea, work through connected examples, practice it, and then check the solution. First up, let's talk about fractions. Imagine we are sharing food fairly. If a pizza is cut into 8 equal slices and you eat 3, how do we write that? That question gives us a reason to care before we calculate. The useful question is not only how many pieces we have, but how many equal pieces make the whole. A fraction compares a part to an equal size whole. Before we touch the symbols, we want to know what the numbers are actually describing. The formula to keep on screen is part over whole, equivalent fractions. A over b equals a xn over bxn. Watch the whole split into equal parts before we attach symbols to it. Let's model this case. Shade 3 out of 8 equal parts. We model it directly, 3 over 8. This builds the mental model before we add more steps. Now we label the picture first, then write the fraction. Now use the same idea in a new case. Write 4 shaded squares out of 10 and simplify. Step by step, the solution is 4 over 10 equals 2 over 5. Notice the order, identify the quantities, write the operation, calculate, and check the result. This is where students often count the wrong object. The denominator names equal parts. It is not the number you ate. The fix is simple. Slow down and ask what each number represents before using a rule. Keep the picture in your head while you try this one. Try this one. Compare 3 over 4 and 5 over 8 using equal denominators. Pause for a moment, solve it with the same model, and then compare your work with the visual. Now compare your answer with the model. Let's finish the set with this case. Add 2 over 3 plus 3 over 5 with a common denominator. The solution is 10 over 15 plus 9 over 15 equals 19 over 15 equals 14 over 15. This case checks whether you can still use the model when the numbers are less friendly. The picture tells us what the numerator and denominator mean. Fractions describe equal parts of a whole. Next, let's move to order of operations. Let's treat this like a calculator mystery. Why do calculators agree that 3 plus 4x2 is 11, not 14? That question gives us a reason to care before we calculate. The rule is a traffic system for operations, so every calculator follows the same route. Order of operations tells us which action comes first. Before we touch the symbols, we want to know what the numbers are actually describing. The formula to keep on screen is PEMDAS. Parentheses, exponents, multiplication over division, addition over subtraction. The screen will tag which operation gets handled first. Let's model this case. Evaluate 3 plus 4x2. We model it directly, 3 plus 8 equals 11. This builds the mental model before we add more steps. We solve it by uncovering one layer at a time. Now use the same idea in a new case. Evaluate 6 plus 2x5. Step by step, the solution is 6 plus 10 equals 16. Notice the order, identify the quantities, write the operation, calculate, and check the result. The trap is reading the expression like a sentence from left to right. Do not simply work left to right when multiplication or parentheses are present. The fix is simple. Slow down and ask what each number represents before using a rule. Try to predict the first move before calculating. Try this one. Evaluate 8(3) x4 plus 6. Pause for a moment, solve it with the same model, and then compare your work with the visual. Now reveal the path and compare it with your prediction. Let's finish the set with this case. Evaluate 18 over 3 plus 3 plus 2 3x4. The solution is 18 over 6 plus 8x4 equals 3 plus 32 equals 35. This case checks whether you can still use the model when the numbers are less friendly. The order is what keeps one expression from having two answers. Order of operations keeps expressions unambiguous. Finally, let's connect that to ratios and proportions. Think about doubling a recipe without changing the taste. If a recipe uses 2 cups of rice for 3 cups of water, how do you double it? That question gives us a reason to care before we calculate. A ratio protects a relationship between two quantities. Ratios compare quantities, and proportions keep comparisons equivalent. Before we touch the symbols, we want to know what the numbers are actually describing. The formula to keep on screen is ratio AB, proportion. A over B equals C over D. The bars grow together so the comparison stays the same. Let's model this case. Double the recipe ratio 2, 3. We model it directly. 2, 3 becomes 4, 6. This builds the mental model before we add more steps. We scale both quantities by the same factor. Now use the same idea in a new case. Scale 5, 2 by 3. Step by step, the solution is 15, 6. Notice the order, identify the quantities, write the operation, calculate, and check the result. The easy mistake is adding instead of multiplying. Do not add the same number to both sides of a ratio when scaling. The fix is simple. Slow down and ask what each number represents before using a rule. Scale the pair, not just one side. Try this one. Find x if 3 over 4 equals x over 20. Pause for a moment, solve it with the same model, and then compare your work with the visual. Now check whether the new comparison still matches the old one. Let's finish the set with this case. A map scale is 3 cm, 50 km. How far is 7? 5 cm. The solution is 7. 5 over 3 equals 2. 5, so 50 x 2. 5 equals 125 km. This case checks whether you can still use the model when the numbers are less friendly. Ratios stay fair when both parts scale together. Ratios compare, proportions preserve the comparison. Let's bring everything together. Today we covered fractions, order of operations, ratios, and proportions in that order. When you study, try to connect each rule to a visual model and one real example. In the next video, we will work on 003. How to master percentages, exponents and roots, and scientific notation.